Okay, so hello everyone. My name is Pengke Li. I'm a PhD student from University of Rochester. Before my presentation, I want to thank the committee for inviting me to give this talk, especially those recommended me as an invited speaker. And to me, of course, it's a great honor. Today, the title of my talk is Spin-orbit Interaction and Spin Relaxation of Conduction Band Electrons in Silicon and Germanium. This work was supervised by Professor Hanan Derry. So here's the outline. At the beginning, I'll introduce the background information related to our research, including recent years' experiment efforts and also the benefits of using silicon for spintronics. And then I'll introduce our work of building an 8x8 Hamiltonian to capture the spin-orbit properties of conduction band electrons in silicon, and then use this model to study the spin relaxation. And at the end, I will show our similar study on germanium. So first of all, I will give a short overview of experiments in recent years on silicon spintronics. In 2007, the experiment of spin injection and detection in silicon was first carried out by Applebaum's group. Spin polarized hot electrons are injected from ferromagnet into pure silicon, and after drifting for hundreds of micrometers, at the detection they still show clear signal of spin polarization, indicating very long spin lifetime. In the same year and the following years, spin tunneling injection was performed by Barry Jonker's group in NRL and also some other groups. Different types of tunneling barriers are used. Spin signals are detected by measuring the circularly polarized luminescence either from box silicon or from silicon germanium quantum well. Similar to gallium arsenide, the lateral spin transport geometry is also used to study heavily doped silicon. The four-terminal non-local measurement of Henle effect is carried out to study spin transport in different temperature ranges. The three-terminal measurement is also carried out by many groups, including Henle measurements in room temperature and even in high temperature up to 500 Kelvin. There are also some other different methods utilized to study silicon spintronics, like the spin tunneling into two-dimensional electron gas, the Seebeck tunneling, the inverse spin Hall effect, and elegant work of spin pumping into p-type sample. All these experiment efforts in silicon spintronics are motivated by the dominant role of silicon in the well-developed semiconductor industry. So in the following section, I will briefly discuss the advantage of using group 4 semiconductor, especially silicon, for spintronics. Silicon in the periodic table has atomic number of 14, which is lighter than most other elements of semiconductor materials, indicating its smaller spin-orbit interaction. So for example, compare the band structure of gallium arsenide and silicon. The split-off energy of silicon is about an order of magnitude smaller than in gallium arsenide. A second feature of silicon is that its crystal lattice possesses a space inversion symmetry. It is known that in compound semiconductors like gallium arsenide, because of the absence of this space inversion symmetry, the dominant spin relaxation mechanism in a wide range of conditions is the Diakonov-Peral mechanism. In silicon, this mechanism does not exist, and the spin information could be kept for a longer time. So instead of dp, the dominant spin relaxation mechanism in silicon is the Elliott-Jaffet mechanism, in which the spin flips from a spin eigenstate to an opposite spin eigenstate. The spin eigenstates are not 100% spin pure due to spin-orbit coupling, but combinations of spin up and spin down components. However, For electrons in the conduction band, the spin eigenstates are very pure. Usually the amplitude of spin majority components are orders of magnitude larger than that of the spin minority component. The Elliott-Jaffet mechanism includes the Elliott and the Jaffet terms. In the Elliott term, the interaction couples the same spin components, while the dominant Jaffet term couples the large and opposite spin components. This spin flip mechanism was initially studied by Elliott and then by Jaffet. By analyzing the space inversion and time reversal symmetry of the system, Jaffet raised the Elliott-Jaffet cancellation, in which the zero and first-order terms of the wave vector vanished, resulting in very long spin lifetime. And for silicon, the temperature dependence of the spin relaxation rate is T to the 5 half. Jaffet's result is valid for spin relaxation by scattering with long wavelength acoustic phonons. However, as we know that silicon is a many-valley semiconductor, and in a recent paper by Cheng et al., intervalley scattering with phonons of large crystal momentum is found to be very important for spin relaxation. These authors use empirical pseudopotential method to calculate the spin relaxation rate and numerically fit it to be T to the third. This result implies that behind numerical calculation, there should be new physics of electron spins in this many-valley semiconductor with elliptical energy surface. Now, I will present our systematic study of spin-orbit interaction, spin-orbit symmetry of conduction electrons in silicon, and recently published in PLL. I will first of all remind you the widely used Kane model for band structures of zinc-blende semiconductors like gallium arsenide. Beyond band structure, this is also a powerful tool to analyze many electronic properties due to its simplicity and precision. In this model, usually 8 wave functions are considered for the basis set, including 1 conduction band and 3 valence bands at the zone center, together with the spin substrates. All of these wave functions have definite parities. The conduction band is even and can be expressed as S. The valence bands are odd and can be expressed as linear combination of X, Y, and Z. Within this selected basis, usually 3 parameters are crucial, because as a model from perturbation theory, there are 3 first-order perturbation terms. The P is related to the K dot P term, delta related to the K-independent spin-orbit interaction, and the alpha to the K-dependent spin-orbit interaction, which is usually much smaller. So go to the case of silicon. We know that the 6 conduction band values lie along the delta axis about 85% from the zone center to the zone edge. Electrons in the values are close to the high symmetric X point, which is the center of the facet. So we consider of taking the states at the X point as basis of the perturbation. Different from the Kane model, at the X point, there is no definite parity, which is very unique. We cannot write the basis as simple forms like S or X, Y, or Z, because the even and odd components are mixed here. In order to apply the perturbation method, we use a more general tool called the method of invariance, which is based on group theory, especially the theory of irreducible representation. It is straightforward to apply this method on X point, which requires the decomposition of the direct product about the irreducible representations of the basis. Here's a character table of the space group of the X point. You don't have to pay much attention on it if you are not familiar with group theory. Don't worry about that. What I want to mention here is that only the last 4, X1 to X4, are possible irreducible representations for electronic states, and all of them are twofold degenerate due to the space inversion and time reversal symmetry. And this degeneracy has nothing to do with spin. On the right is the table of invariants. These invariant components and matrices are derived straightforwardly from the operators of the space group up to the first order perturbation. Now, I'll give an easy example of using this table to construct a Hamiltonian of the conduction band. The conduction band basis belongs to x1. So we take the direct product of x1 and then decompose it as the sum of 4 representations. Then we associate the corresponding invariant components and invariant matrices accordingly. For example, we have M1. So we just take the k square times the identity matrix with a factor of A. And also we have M3 prime. So we take kz times the matrix of row z with a factor of B. Here in the decomposition, there are two other representations, M2 prime and M4. But they correspond to higher order of perturbations not listed in this table, so here we don't have to take them into account. So here's the matrix form, and the parameter A is about universal constants, and B is related to the position of the bottom of the conduction band, which is about 15% of the delta axis from the x point. Now let's take a look at the matrix of the coupling between the conduction band and valence band, which is the most important part, because we know that most of the spin-orbit interaction is from the valence band, which belongs to x4. So following the same procedure, we can see that the direct product of x1 and x4 is m5 plus m5 prime. These two representations transform as vectors and pseudo-vectors respectively. Then we just construct a Hamiltonian by taking the k dot p term, the k-dependent spin-orbit interaction, and finally the k-dependent spin-orbit term. Pay attention at this term that has the form of k times sigma, which looks very similar to the Rashba term in systems without structural immersion symmetry. However, this term is from the k-dependent spin-orbit perturbation and has nothing to do with the Rashba term. If using the load-in perturbation method to fold this term into the HCC conduction band matrix, it turns out that it doesn't induce any spin splitting as the Rashba term does. But this really makes sense because space inversion and time reversal symmetries are kept here. Moreover, later on we'll show that this term is much smaller compared with P, and in fact the delta x related to the k-independent term will turn out to be the most important spin-orbit interaction, whereas that alpha is just a small correction of it. So here's the matrix form, and for all the three parameters, P is taken from experiment results of the transverse effective mass of conduction band electrons. The two spin-related parameters in red color are calculated by empirical pseudo-potential method. So by putting this matrix blocks all together, we can construct a total Hamiltonian by putting the Hermitian conjugate of HVC, and then we fill in the matrix elements of the valence band by approximately taking the direct band gap, which is much larger than all other elements, because our focus is on the conduction band rather than in details about the valence band. So up to this point, we build the 8x8 matrix to describe the conduction band electrons of silicon. And first of all, we examine its validity by solving the eigenvalue problem. So we get the expressions of the energy band compared with the dashed line in this figure by numerical pseudo-potential. And also we get analytical expressions of the eigenstates, which are of course 1 by A vectors. This 1 by A vectors looks to be complicated at a first glance, but here please don't go into details of these 8 terms. Rather, I will just use them to calculate the so-called spin mixing, which is the total probability of the spin minority components. So first of all, let's take a look at the facet of the Brillouin zone, where the spin mixing was calculated numerically by these authors. So along major axis on the facet, there are highly spin mixed states in which the ratio of the two spin components is close to 50 to 50. And we found that these spin hotspots can be captured in this equation calculated from the expression of the states, and it actually produced the same result. If we go back to the expression of the energy band, the inside of these so-called spin hotspots is actually shown clearly by the splitting term. So on the Brillouin zone facet, Kz is 0. And along either x or y axis, the kx times ky term is also vanished. So only the term with delta x remains, meaning that the broken degeneracy of the two conduction bands is totally induced by spin orbit, and this is the origin of these highly spin mixed states. Similarly, we give the expressions of spin mixing at the bottom of the conduction band, and again it matches well with numerical result. So by checking both the energy band and eigenstates, we can say that this 8 by 8 Hamiltonian can precisely describe the spin properties of conduction band electrons. Moreover, only this 8 by 8 is enough, because other bands are too far away in energy, and also because the spin-orbit interaction on conduction band electron is again mostly from the X4 valence band. So after introducing our model of 8 by 8 Hamiltonian, I'll show an example of using this model to study spin relaxation by scattering with phonons. So in this Elliott-Jaffet process, the transition described by this matrix element is from a state at K prime through electron-phonon interaction to a state at K with opposite spin. So considering its many-valley property, there could be first of all intra-valley transition, where K and K prime are within the same valley, and also inter-valley transition, where K and K prime can lie in two different valleys along the same axis, called the G process, and also in valleys along different axes, called the F process. A good merit of our model is that the Elliott-Jaffet cancellation is already built in this 8 by 8 Hamiltonian, and after the cancellation, the Elliott term has much larger contribution than the Jaffet term. A more comprehensive analysis will be presented by Mr. Yang Song in the following talk. Here I will just show how the Elliott term is working in our model. So first of all, intra-valley spin relaxation. Here are the states at K and K prime. So instead of these complete forms, I will show you a more compact form that captures important features. So we put arrows indicating the spin directions and with the size representing the amplitudes. So the major contribution of the Elliott term is the dominant coefficient of 1 coupled to components with the same spin. For example, with the valence band. However, in this case, these k-independent coefficients cancel with each other due to the orthogonality of the bases and giving zero result. On the other hand, the coupling to the conduction band itself is possible via dilation and shear deformation potential, and the matrix element scales as 1 over Eg, which is the direct band gap. Also, the coupling to upper conduction band is possible, where the off-diagonal deformation potential, which is responsible for the splitting of the degeneracy at the X point, if off-diagonal stress is applied. And this coupling scales as 1 over delta C, which is the energy difference of the lower and upper conduction bands, about an order of magnitude smaller than the direct band gap, meaning that this coupling is much larger than the previous one. So we conclude that for intravalley spin flip transition, it is governed by the coupling between the lower and upper conduction bands. And from the phonon dispersion relation, we can see that long wavelength acoustic phonons are involved. Furthermore, the matrix element, which is proportional to the difference of K and K prime in the transverse direction, indicates that the transverse acoustic phonon is involved. So the K quadratic matrix element arrives at Jaffet's prediction of 5-half temperature dependence of the spin relaxation rate. Secondly, the G process. This is the scattering between neighboring values on the same axis by phonons with wave vector about 30% along the delta axis. For example, here's the state from Z valley to minus Z valley, in which the upper and lower conduction band bases interchange with each other. And this is actually the same as in the next Brillouin zone, where the lower conduction band no longer belongs to delta 1, but delta 2 prime. So again, we put the arrows representing spinning amplitudes. And in this case, the direct coupling by the dilation and shear deformation potential is dominant. So considering the interchange of the bases I mentioned just now, it is actually the coupling from the lower conduction band of one valley to the upper conduction band of the opposite valley. And also here we give the matrix element and also the temperature dependence of the spin relaxation rate. Then we switch to the F process. In this case, the X point of different axes are involved, so the bases of the bra and cat are no longer orthogonal, whereas there would be a large overlap between conduction and valence band of bases along different axes. And this can be understood by the concept in the tight bundling method. For example, here's the transition from the Z valley to the X valley. Take a look at the illustration of bands on the right. In the Z valley, the conduction band has a large component of Z, while the valence band has X and Y. Go to the X valley, the conduction band is X, and the valence bands Y and Z. So the coupling between the conduction and valence bands could be pretty strong. So following the same procedure, we can see that in this case the X1 to X4 coupling is no longer destructive but constructive. So this K-independent coupling of the conduction and valence band is the dominant contribution for the F process spin relaxation, governed by the sigma phonon. And our analysis shows that among the 4 different phonon modes of the sigma phonon, only sigma 2 and sigma 3 are allowed if the transition is perpendicular to the spin direction, while otherwise sigma 1 phonon is also allowed. And finally, we give the matrix element which is independent of K, and also the temperature dependence of spin relaxation rate. And we summarize all the 3 processes by plotting the spin lifetime resulted from each of them independently. It turns out that in this figure, the F process by the red curve gives the shortest spin lifetime, which is the major effect above 50 Kelvin. where the sigma phonons begin to play a role. The T to the 5 half relation by Jafet only appears at low temperature for pure sample and would be easily ruined by effects like the impurity scattering or by hyperfine interaction. The sum of these three processes is plotted by the black curve, which matches well with cross marks of experiment results of electron spin resonance by the Pine and Lancaster and hot spin injection by Applebaum. Spin lifetime at room temperature by phonon scattering is about 10 nanoseconds. And we examine all the phonon modes related to each process of spin flip transition, together with the phonons responsible to the momentum relaxation. And because these two quantum transitions are of different mechanisms, of course they are governed by different selection rules, so the involved phonons are different. And at the end, I'll show our similar study on germanium. Following its counterpart of silicon, in the recent 2 years, germanium is attracting more and more attention in the community of spintronics. I'm sorry that I don't have enough time to mention all these experiment efforts one by one, but just as introduced in the previous talk, that germanium is also a well-developed material in semiconductor industry, especially it has promising potential in optical application. It could also be an interesting and important material in spintronics. Different from the X point in silicon, in germanium, the conduction band values located around the L point of the brilliant zone. If we examine the detailed band structure of this L point, we'll find that the conduction band belongs to the representation of L1, while the valence band belongs to L3 prime, and the closest upper conduction band belongs to L3, which is not far away in energy. It's around 3.3 electron volt, while the band gap is just 2.2 electron volt. Both L3 and L3 prime are two-fold degenerate, so together with the spin subspace, we can construct a 10 by 10 Hamiltonian, as we do on the 8 by 8 Hamiltonian for silicon. And this 10 by 10 Hamiltonian is also very concise and analytical. Here, I'm not going to follow the same procedure again. Instead, I'll just show you some of its major difference with the X point of silicon, and also the resulted interesting physics. An important feature of the L point is that it has definite parity under inversion, in which the conduction bands are even, while the valence band is odd. With the existence of the spin-orbit perturbation, the upper and lower conduction bands are coupled by the K-independent term, while the coupling of the conduction and valence band is by the K-dependent term. Pay attention at this gradient of V cross P and cross K. It is known that usually P is much larger than H bar times K, indicating that the effect of spin-orbit interaction from upper conduction band is much stronger than from the valence band. So go to the spin relaxation. So in the spin relaxation, the intravalley scattering is between the conduction band and valence band, while the upper conduction band doesn't play a role because, similar to the intravalley scattering in silicon, the K-independent coefficients cancel with each other due to the orthogonality of the bases. The difference is that in silicon, this process couples the lower and upper conduction band. On the other hand, those K-independent terms kicks in intervalley transition because bases there are no longer orthogonal, and this is also similar to the case in silicon, while there the coupling is between the conduction and valence band, and here in germanium it is the coupling between lower and upper conduction bands. So here's a summary of our result for silicon spintronics, spin relaxation in germanium. Again, the selection rules for spin flip scattering and momentum scattering are different. In intravalley spin flip scattering, TA phonon has a larger contribution than LA phonon, while for momentum scattering, LA is much more important due to the anisotropy of the effective mass. For intervalley process, we know that only X1 is allowed for momentum scattering, while in the spin flip scattering, X3 and X4 are also allowed. Also, we give the expressions of spin relaxation rate, which matches well with numerical result of pseudo-potential. In the case of intravalley, the T to the 7/2 relation predicted by Yafet is a result of the k-cubic dependence of the matrix element. However, the exponential relation of the intervalley transition determines the spin lifetime, giving only 1 nanosecond at room temperature. Remember, in silicon, the intervalley scattering becomes important if the temperature is above 50 Kelvin. Here in germanium, this mechanism starts being dominant from a lower temperature of just 20 Kelvin. And this can be understood by considering the lower energy of the X1 phonons of germanium, which is about half of the energy of the sigma-1 phonons in silicon. Another reason is that the T to the 7/2 dependence of intravalley spin relaxation is even weaker in lower temperature. And that's all my talk. Thank you for your attention. Here's a short summary of this talk, and please go to the reference for details. Thank you very much.